Hello and good day everyone. Meet myself. I'm Dina, metric number MA19218. It is my pleasure to meet you all here and to our beloved lecturer Dr. Norizato. So we are here to give a presentation regarding on experiment heat transfer 1, which is known as the heat conduction. So there are two things that we are about to consider. The first one is the linear conduction and followed by the radial conduction as well. So let us see. So before conducting an experiment, we need to get to an understanding what is about heat conduction is. So we can say that the thermal conduction is a mode of heat transfer that occurs in a material through a temperature gradient. So in both liquid and gases, it exhibits excessive conductive heat transfer. So we can say that solids are chosen to exhibit pure conductivity. Also in practice, the thermal conductivity will be appear in three dimensions, which analyzes its complexity often requires extensive calculations. So in one-dimensional approach, it is very needed in a laboratory to demonstrate the fundamental laws which relates the heat flow rates to temperature gradients and areas. So let us see the first part, which is known as the linear conduction heat transfer. So as we can see in the figure, it shows a linear temperature distribution in the same particular solid material. We can say that it is necessary to estimate the heat flux through a solid when the flux is not constant. For example, like a walls is heated through a cooled furnace. So the calculating the heat flux under this conduction, we can say it requires a finding temperature distribution of a solid and how the distribution will change. So the instrument setup already described facilitates and transient conductivity studies as changes in the temperature profile which can easily monitor during heating or cooling cycles. Also in linear heat conduction, there are specific things that we need to consider as well. As we can see in figure 2, it shows a linear temperature distribution of a different solid material. So we can say that the continuity of heat flow rate is the same for each section of the conductor, which shows the thermal conductivity is constant, which assumes no change with average temperature of the material. So in figure 3, we can say that the linear temperature distribution with various cross-sectional has some difference on it. So which concludes that the rate of heat conduction is proportional to the temperature difference across the layer and the heat area transfer, but is inversely proportional to the thickness of the layer. So based on this observation, we can come up with a formula which is shown in the Fourier's law of heat conduction. As we can see, the heat rate of conduction is equals to the product of the thermal conductivity with the area of the cross section of the conduction together with the division of the changes in temperature over the changes of displacement between 2 points. Okay, now let us focus on the theoretical aspect of radial conduction of heat transfer, which is normally portrayed in a cylindrical way. So based on the figure 4, it shows a picture on radial temperature distribution. So we can say that the inner and the outer surfaces of the thick walled cylinder would be at the same temperature, which the heat will be transferred radially through the cylinder wall. So for continuity reasons, the radial heat flux through a successive layers of the wall would be constant if the flux is stable, but the temperature gradient would be decreased with increasing radius since the area of the successive layers increases with increasing radius. So based on the theoretical observation of an radial heat conduction, we come up with a formula to obtain the amount of heat which is conducted across the cylinder wall per unit time. As you can see here, the formula consists of the thickness of material, thermal conductivity, the inner section of the temperature together with the outer section, and we need to include the outer radius and the inner radius as well in the formula itself. Okay, since we had covered the theoretical aspect of linear and heat conduction analysis, so let us focus on the experimental apparatus that we have used to conduct this kind of experiment. So as we can see in the figure 6, it shows an unit assembly for heat conduction study bench model. So the instrument includes two thermally conductive samples. The first one is the for linear testing conductivity, which has a multi-section rod, as you can see in the picture. And for radial conductivity, we would be using a metal disc in the apparatus itself. So the control panel will provide and electrical and digital power to the sample, display heater, as well to select switches for the data acquisition system. So this apparatus has a small flow of coolant which provides heat dissipation at the end of the part for each sample.
Assalamualaikum and hi. My name Mohamad Eizzat bin ZAHEERRUDDIN, matrix number MA19259. I will present about 3.0 experimental procedure. This experiment procedure is divided into two parts, where experiment A, linear module, and experiment B, radial module. For experiment A, linear module, the first is to make sure the main switch is initially off. Then insert a brass conductor into a linear module and clamp together. The second step is check at interval. Then turn the heater power to a fully anti-clockwise position and connect the sensor leads after that. After that, load to experiment software. Lastly, turn the heat power control to 20 watts and record the temperature at all switch points and the input power reading. For experiment B, radial module, the only step that has been changed were step 4. Step 4 says to connect the seat sensor lead, the plugs on the top of the linear conduction module. Connect the left hand sensor leads from the module to the place. All the next steps are same with the experiment A. Then 4.0 is talking about data analysis. I will explain question A, B and C. For question A is about the experimental datasheet. For question B is plotting the graph of temperature versus distance. For question C is plotting the graph of temperature versus ln x. This experiment will be conducted at experiment A and B. This is the answer for experiment A. We use stainless steel. From this datasheet, we can plot the graph temperature versus distance. This graph shows the linear distribution of stainless steel and elements. And question C is plotting the graph of temperature versus ln x, shows the significant increase every watt. Next, this is the answer for experiment A. We use brass element. This is the data sheet. From this data sheet, we can plot the graph temperature versus distance, which shows decrease and maintain. This graph shows the linear distribution of brass element. And question C is plotting the graph of temperature versus ln x to show the increase of every watt. Lastly, this is the answer for experiment B. We use brass element. From this data sheet, we can plot the graph of temperature versus distance. This graph shows the linear distribution of brass elements. And question C is plotting the graph of temperature versus ln x, shows the increase every watt. That's all from me. Thank you.
Hi, Assalamualaikum. My name is MOHAMAD AISAMUDDIN HANIM bin YUSOFF, matric number MA19250. So now I will continue 4.0, which is in data analysis in part D and part E. First, how to calculate the gradient dt over dx values for each sample. As we all mentioned, the linear conduction calculation, we need have two point, which is we assume that take point 1, 2, 3. So there is 4 type of heater, which is in 5 watt, 10 watt, 15 watt and 20 watt. So we use the formula dt over dx equivalent to lambda t over lambda x equivalent to difference of temperature over difference of x. So it will be lambda t over lambda x equivalent to difference of temperature 3 and temperature 1, which is in 33.17 minus 30.37 over 0.03 minus 0.01. So the answer will be 140. So we get the temperature of the power of 5 watt. Same way for the next, for the specimen of the brass, we need to use the result of a brass specimen, which is in also same in there have 5 heat, which is in 5 watt, 10 watt, 15 watt, and 20 watt. So we got the lambda t over lambda x for 5 watt is 136 degree. For the radial conduction calculation for brass, the result have been given in the table. So we just put all the result into the equation that using the formula dt over dx equivalent to lambda t over lambda x equivalent to the difference of temperature over the difference of x. So all the x, we assume that we take the point 1 to 3. So next, part E, which is in calculate the K, the thermal conductivity in value for each experiment. So in linear conduction calculation, we have been given the diameter is 0.02. What we need is to find the area. Area formula is A equivalent to pi d squared over 4. So we got the area is 4.9087 times 10 power of negative 4. So the Q is not been issued because it was being given in the question. So we have formula for K, the thermal conductivity, which is Q multiplied by x3 minus x1 divided by area multiplied by T1 minus T3. For stainless steels, so we got the Q is 5 watt. Then we need to substitute all the values in the formula of K, which is K equivalent to 5. 5 is Q and 0.03 minus 0.01 for the X point we assume divide by area and multiply with temperature of the difference of the temperature. For the brass also, we need to have same equation for the K, which is K equivalent to Q. Q is 5 and the X 0.03 minus 0.01 divided by 4.9087 is the area and times with the difference of T1 and T3. And then we got the answer of the brass in 5 watt 74.8970. And they are same way, but the difference is in the temperature, which is temperature for stainless steel. We had the result have been given before, and brass the result have been given before. Then to calculate the radial conduction, we have been given the length 0.003 meter, R2 is 0.02 meter, R9 is 0.07 meter. Why we use R2 and R9? Because the inner section temperature, which is Ti, represent the temperature T2, right? Whereas the outer section temperature, which is T0, represent the temperature at T9. Alright, so the formula have been given Q, not our issue because have been given, and we use the formula of K to calculate the power in 5 watt.
Assalamualaikum warahmatullahi wabarakatuh. My name is Irsyad and I will be present for the topic discussion for question A and B. For the first discussion, compare the calculated thermal conductivity to its typical value and describe the discrepancy factor. For the experiment A, brass and stainless steel specimen for linear conduction. Based on the above calculations, brass has higher thermal conductivity than stainless steel in both power input in the linear conduction experiment. It is because of the various elemental composition which affect the rate of heat conduction. So, from the experiment conducted, brass will have higher conductivity than steel. We proved that our results are accurate theoretically. All the readings were recorded twice to obtain the average temperature. The average temperature will be recorded to reduce this error. The thermal conductivity of a material is inversely proportional to the temperature gradient, according to the Fourier's law. In short, the higher the temperature decrease between two connected elements of the same dimension connected to hot and cold reservoir, the lower the thermal conductivity. When comparing the two materials to be connected with increased power input, larger power will undoubtedly generate more heat conducted along the homogeneous and composite bar, contributing to the higher thermal conductivity. For the second experiment B, brass specimen for radial conduction, based on radial conduction experiment B for brass element, the experimentally result of both thermal conductivities of radial and linear are slightly different. This is because K is only slightly impacted by power P and the temperature change dt during the experimental process. Temperature changes may be slightly inaccurate due to environmental factors and the time required to cool the system down following the previous experiment. Thermal diffusivity is related to thermal conductivity and inversely proportional to heat storage capacity. Also, because the area of subsequent layers grows with radius and temperature gradient must decrease with radius as demonstrated by the radial temperature distribution graph, which shows a slight change in temperature between points but at a nearly constant pace. As a result, thermal conductivity can be increased since, according to Fourier's law, the temperature difference is inversely proportional to K. For the discussion B, why the system of heat conduction experiment requires cooling water flow. Slight cooling water flow provides a heat sink at the end of the conducting path in each specimen. It acts as a passive heat exchanger which conducts heat generated by the electronic system to a fluid medium, typically liquid coolant. It is dissipated away from the device, allowing temperature adjustment. The cooling water flows enables thermal energy transfer from the higher temperature device to a lower temperature fluid medium. The cooling water flow also removes unwanted heat generation in the system, protecting the heat conduction system. Also, the heat conduction system will run under high efficiency condition due to cooling water flow throughout the operation. Cooling water flow also can sustain and maintain specific temperature over time. So that's all for me. We proceed to the next.
Hi, my name is NURAYU BINTI AZHAR, my metric number MA19253. Okay, on this slide I was presenting about discussion number C and D, also conclusion and reference. First question on discussion is C. State 3 reasons why thermal conductivity value for particular material is important in engineering. Okay, first, the terminal conductivity value for the particular material able an engineer to select a suitable material based on requirement needs. Terminal conductivity is a critical property of mineral and element that is required for the engineering of the infinite number of technologies and tools. Selecting a material with a apposite conductivity rating can exchange the product efficient and save the energy. Okay, second, reason on the terminal conductive value is a material attribute. The use of terminal conductivity is material dependent. Terminal conductive is a property of a substance that determines whether it is a good conductor of heat or not. As a result, the material can be analyzed as a heat conductor or an insulator. Okay, lastly, terminal conductive value for a particular material is essential in engineering due to the application in industry approach. The terminal conductive is used to determine its capacitance to conduct heat. Okay. For discussion D, give 3 examples of heat insulation method that being used in engineering nowadays. Okay, first, blanket insulation. The most common insulation method used is blanket insulation, which come in the form of bags or rolls. Blanket insulation is often put in area where there are no obstruction, such as unfinished wall, floor, and ceiling. Okay, second, insulation board. The insulation board method are utilized for internal wall lining or partition wall. They come in a variety of size and thickness. When they put continuously over frame or joints, it can prevent thermal short circuit. Okay, number 3, reflecting sheet material. The reflecting sheet material have high reflectivity and a low emission rate, making them heat resistant. The reflective insulation method can include gypsum board, steel sheet reflection material, aluminum foil, sheet aluminum reflection material, and other material. Okay, for the conclusion, brass has better thermal conductivity than stainless steel in all power input experiment for linear conduction. Based on the result, the thermal conduction value obtained in stainless steel for every power value are lower than the brass element. Thermal conductivity is a variable that transfers the quality of heat from one location to another as the temperature change. As the result, it is superior thermal conductivity. Brass has a fast heat transfer in a given distance over temperature fluctuation than stainless steel. Okay, for the thermal conduction occur when heat moves from a other region to a cool zone. The heat conductivity of stainless steel and brass was estimated, with brass having a higher thermal conductivity than steel. Brass has a better thermal conductivity in radial flow than the linear flow for variable heat flow. For reference, first we using heat transfer from Chengal 2003. Second revision, we use thermodynamic and engineering approach 7 edition. And third, thermal insulation definition, material and method from 2020. Okay, that's all. Thank you.